Welcome back. We're going to be taking a look at some practical applications of the integral and how we can put in some of our physics ideas into this and have hopefully some real fun with this. I rather enjoy this one. So let's take a look. We are going to start off with just a simple acceleration that is constant. For example, it could be that we are on Earth and we have 9.82 meters per second squared. It could be something else, though. It doesn't have to be Earth, but if that helps your mind, then let it be Earth. All right, we have an acceleration, and with time, that would be right here. The acceleration is constant, therefore you have a nice flat line. As time goes by, the acceleration is not changing. So you could take a look at any time interval and you would see that, well, nothing's happening. It's just the acceleration's there. However, as you know, when you have, say, a ball in your hand and you let it go and you know what the acceleration is, you know that for every second that passes, something happens. The ball is picking up a velocity. It is increasing its velocity and it is changing its position. So how the area under this line here will then show us what is happening. And think to yourself, what is acceleration times time? Well, that's going to give you the velocity. If you have 1 second go by, then the area right here will be the velocity at that time. So that being said, let's take another look here. If we integrate this acceleration, we will get the area under this particular, well, in this case, this little flat function there, but just because it's flat and easy to take the area of manually, we know how to get a rectangle. We're going to do this the long, nice way because now we know how to integrate things. So if you integrate a with respect to time, this is what is going to happen. I have a bit of a cold, so excuse my stuffy nose here. Okay, we already knew that this area here was going to be the velocity for any given moment in time. So if we integrate this, now area is what's being integrated. The dt is just the change in time. Remember the little disks that we're thinking about when we integrate. It's just the change in time, or time times acceleration, gives us what we're looking for. Now, don't be afraid of this. See, the standard simple integration would be just that, the a times t. Now, sometimes you may have an initial velocity with something. This initial velocity in our rock in hand case was 0. We hold the rock, we open our palm, the rock falls out of it. Okay, it started off with a 0 velocity, but it doesn't have to start off. The v naught gives us the general formula for this, so that we don't have to be worried about it in the case of the rock in our hand. But other times we want this, so it's good that you see where it comes from. Okay, let's take the next one. What do we get when we draw a graph of it? Well, we're used to a velocity time graph. Remember, time is this way, and then this is how velocity is increasing. And just like with the acceleration graph, the area under the curve will represent something. But remember, let's look at this time right here. Let's say it was 2 seconds. Then the same corresponding 2 seconds, this area would be this value, okay? Assuming we did them to scale and everything was correct. Now I just drew little pictures, but that's the idea. All right, let's continue. We also know that the area under a velocity time curve will give us information. So what could that information be? Well, think to yourself, if you're driving down the street in a car, you're doing 100 meters per second, how far have you gone in 1 second? in 2 seconds, in 3 seconds, okay? Well, that's the same thing. But let's do integration, because we know if we have a linear function, we know we can take the integral of it, and we know you'll then get the area under the curve. So let's do that. We want to integrate the velocity to get a position, a place. Where are we from when we started before? All right, let's see what happens. The position, y, will be the integral of the velocity with respect to time. So what do we need to do? Well, we know the velocity. We already calculated it. We said the velocity was this, or in simple terms, it could just be at, but we'll go ahead and do the general. So what happens? Well, we write it up, okay? We take the next step, and then we get a second degree equation. Don't be alarmed by this big thing here. Just remember that this term here goes to there, this term goes to there, all right? And then this just means that you don't have to start out at a 0 position. In the case of the stone leaving our hand, yeah, we say that we can let that be the origin. And we say, okay, we start off at 0. But it doesn't have to, just like the velocity doesn't have to start at 0. Position doesn't either. All right, so how does that look? What kind of curve do we get when we have a second degree, which this is? Well, that's easy. You've all seen those before. So we have a YT graph. So what do we know about it? Well, everything follows everything. If whatever time interval you're looking at, if you're looking from there to there and there to there, ignore my sort of straight lines there. All right, the point is that we have the same time frame. This place will be the distance traveled, which will correspond to the area there. This velocity will correspond to the area there. So everything is connected. I find that fascinating. I always loved that when I learned it the first time. I thought, gee, this is cool. This is neat. All right, let's put our latest formula on the other side, and we'll take another approach, because you have seen this formula in the physics book, and now you have seen one way to get it. All right, what happens if we now take the derivative of this? Well, you know from before, and you know from early calculus, that if you take the derivative of a second degree function for a particular time, you'll get the slope of the tangent at that point. And that will give you the instantaneous velocity. So we kind of expect something like that to happen. So let's take the derivative. Let's see what we get. All right. We know that when we take this and we take the derivative of it, this could, for our purposes, could just be 0 or a constant. But the derivative of a constant is just 0 anyway. What's the derivative of v naught t? Well, you're going to get that. What is the derivative of this? Well, the 2 comes down, plays with the 1/2, you end up with just that. Okay, so we got everything we expected. We expected to find a velocity. So the derivative of a position function gives you the velocity, and we can ask the same question, well, what happens when we take the derivative of a velocity function? Well, we're about to find out, and I think you already know the answer. Here it is. The derivative of the velocity with respect to time is acceleration. And we're not surprised when that's what we're taking the derivative of. Okay? The velocity, the initial velocity in our stone in hand case was 0, but even if it was 2 or something, the derivative of a constant is nothing. That'll just go away. But the derivative of this is that, because it's with respect to time. See, dt. So there's our time. So the derivative of at is just a. So we end up back where we started. We took a whole ride around the block. We did a square circle. We started off with a constant of acceleration. We go up, take the integral, we get the velocity. We take the integral again, and we get the position. We take the derivative of the position, we get the velocity. Take the derivative of the velocity, we get acceleration. Well, I hope that helps. I'll be doing another part with some more complicated integrals where you might have to think once or twice. And I'll see you next time.